Welcome. We are now ready to learn about something called an ANOVA test. So ANOVA stands for Analysis of Variance, but let me introduce what it's used for by looking at this example. So this is an example comparing satisfaction ratings of teachers randomly assigned to either a public school, a private school, or a charter school. So what we'll be looking at is to determine if there is a significant difference in the mean satisfaction rating among those three populations. So a one-way ANOVA test is used to test a claim of a significant difference in at least one of these means. So when we have three or more populations under consideration, this is when we conduct an ANOVA test. We say there's one factor involved, so the only factor we're considering concerning satisfaction is which type of school they teach at. So no other factors like where the school is located or how long the teacher's been teaching. Nothing else will be looked at except one factor, so type of school. And we say that that factor has three levels, or they're also called treatments, and that's because we have three types of schools. All right, ANOVA has a lot of vocabulary associated to it, and the formulas for calculating the values that are involved in ANOVA can be quite daunting. So in this first page, we're just going to try to give you a general feel for what ANOVA is, and then we're going to be making use of our technology to help us skip over some of the calculations. So we're going to need some variables, and hang in there through this first part as we're just trying to sort of get an understanding about why they call it an ANOVA test. And let us first, I think, write our hypotheses here. So let me scroll down a bit for you. All right, so our alternative hypothesis is just written in English here. So we're wondering if at least one of these populations has a mean that's different from the others. So our null hypothesis will be that there is no difference in the mean among the populations. So satisfaction rating of teachers that teach at public schools is equal to the mean satisfaction for those that teach at private schools, and that's equal to the mean satisfaction of those that teach at charter schools. And we're wondering if there's evidence that actually at least one of these population means differs from the others. So that is the purpose of conducting an ANOVA test, looking for that evidence that at least one mean differs. Okay, so let me come back up to the top here and discuss variables. So K is going to be the number of populations under consideration. They're also called treatments. So K in our case, we have 1, 2, 3 different populations. So K is 3. Lowercase n here, sample size. And for the purposes of creating an easy example to work with, we're going to have a sample size of 5. So same sample size for each of these populations. And then capital N here is going to represent the grand total number of observations. So if we put all of our data together in total, I would have 15 data values. Okay, so as we begin conducting an ANOVA test, there are certain assumptions here that need to be met. The first one is that the populations have the same variance. Now, I know we don't deal with variance a lot in this course, so let's just sort of think of variance as measuring variation in a data set from its mean. So we're going to assume, even though we don't know the means of the populations, that the variation in satisfaction ratings at public schools is equal to the variation at private schools is equal to the variation at charter schools. So that assumption is part of the reason that this test is called an ANOVA test. And let's look at our second assumption. The populations are normally distributed. So if we look at the data from each school, it would be a bell-shaped curve for the population, and all samples are independent. All right, variance for a sample, I have the formula here. So variance is called a mean square. So we'll talk about what that means a little bit. So the symbol for sample variance is S squared. And we're going to look at a calculation here that we saw just once earlier in the semester. And we're going to take a look at it by hand a little bit first, just again, kind of give you a feel for what we're doing. So in the numerator, we're going to be adding a value that's been squared. We call it a sum of squares. We'll do that in a moment. And a mean square is taking a sum of the squares, and we divide by the degrees of freedom. So we will step through that process here, starting with our public schools. All right, so first, if you would like to pause and get this information into the calculator, I'm going to go to my list, so stat edit. So I've entered my public school teacher satisfactions there in L1, private L2, and charter L3. So if you want to, again, pause and do that. And then when we come back here, just clearing my screen, and I'm going to start with my public schools. So first, I'd like to know for this sample, what was the mean satisfaction rating? So I'm just going to do this one by hand. So we know to find the mean, we add the data values. That will be 30. 5 values, so divide by 5. So average satisfaction there is 6. And then I'll just fill in the other ones. You don't have to do the calculation here. The sample mean for our private schools will come out to be 9. And the satisfaction rating for our teachers at charter schools comes out to be 6. All right. So back to our public schools. So we're interested in the squared deviation from the mean for each of those values. So this teacher that said they had a satisfaction rating of 4, I'm going to see how different that is from the group sample mean, which was 6. So that's deviation from the mean, and we square it, and that's called squared deviation. So this is going to be -2 squared, which is 4. So basically, I'm doing the numerator of the formula. All right, I'll just write down the others. So the second one is the same value for that teacher, so that's still 4. And then the next teacher had a satisfaction rating of 6 compared to the group average. There is no deviation there. And then 8 minus 6 squared will again be 4. And 8 minus 6 squared will again. And don't worry, we're not going to have to do these calculations by hand once we get moving. This is just, again, to give you a feel for this formula and what's happening. So the sum of the squares means add up all those values, and that will be 16. Okay, so we could do that for each one again, but just to kind of move us along here, I'm just going to write down the results of those calculations for my private schools. Those will be 0, 1, 1, 1, 1. And then we just abbreviate the sum. Sorry. Try that again. Okay. So when we add those numbers, we just abbreviate it the sum of the squares. So those resulted from squaring the deviations. That's going to be 4. And then I'll come over here, and if you did that for your charter school values, that will be 0, 0, 0, 1, 1. And the sum of the squares, adding those values, comes out to be 2. All right, so in analysis of variance, we are going to look at some of the components of the formula that is needed. And let me start with this statement. If we pooling just means put all of the data together, those 15 observations, then the overall grand mean, so the average of all 15 observations, can be found using this formula, where we take our sample means, so 6 for public, 9 for private, sample mean 6 again for charter. And there's 3 of those. And if we divide that by 3, that will give us the grand mean, so the overall mean. So if I take 6 plus 9 plus 6, divide that by 3, that will give us an average of 7. All right, so with ANOVA, we're trying to gather evidence that there's a significant difference in at least one population mean from the others. So I do see here in the sample that one of them does differ from the other two. We're going to see if this is enough evidence to make that conclusion for the whole population. So the way ANOVA works is we end up estimating the population variance that we've assumed they have in common in 2 different ways. So variation here can be measured between the groups versus within the groups. So it's 2 ways of measuring that population standard deviation. And I'm going to step through a calculation here that, again, we're not going to have to worry about later doing ourselves by hand. I just need to kind of give you a feel for what's happening, because we end up comparing these 2 estimates for the variance in order to make a decision about the means of the populations. All right, so the sum of the squares between the data versus the sum of the squares within the data. So let me start with within. So the sum of the squares within the data. So our sum of squares within the public schools was 16. The sum of the squares within our private schools was 4. And then the sum of the squares within our charter schools was 2. So if we add up all those values, that's called the sum of the squares within the data. For the sum of the squares between the data, we actually compare each of our sample means to the grand mean of the pooled data. So that expression inside the parentheses is measuring each of those sample means compared to the grand mean. It gets multiplied by 5 because the sample size was 5 in each case, and that ends up coming out to be 30. So it's 2 ways of looking at variation in the data. So between the groups is basically looking at sample means compared to the grand mean. Within the groups is just looking at each group on its own within its population from which the samples were drawn. All right, so again, that may seem not crystal clear. It doesn't have to be. Just trying to get you a feel for what we're measuring. So along with that, we're going to end up having associated degrees of freedom with each of those measurements. So in the case of the sum of the squares between, we'll be looking at a degrees of freedom equal to k minus 1. So k was the number of populations. So we had 3 populations in this case. So minus 1 is 2 degrees of freedom. For the sum of the squares within the data, the corresponding degrees of freedom is capital N. That was our grand total of 15 numbers. And we subtract the number of populations. Okay, and then our next step is to find the mean square. So a mean square is always a sum of squares divided by its degrees of freedom. And so I'm just going to scroll up to the top here. So this is what we're doing. The sum of squares divided by the degrees of freedom. So we're attempting to estimate the common variance by looking at 2 ways of estimating it, and then we compare the results of those 2 different ways of estimating variation. The results of an ANOVA test are summarized in an ANOVA table. So this part at the bottom, our calculator is going to be able to do the whole thing for us without going into all the detail that I just did above. But again, just trying to give you a feel for the process. So let me fill in some of these values. So if we say between group variation or variation within the treatments or populations, the between groups is looking at that value with a sum of the squares of 30. its degrees of freedom was 2. So a mean square is a sum of squares divided by degrees of freedom. In this case, 30 divided by 2 gives us 15. The within source of variation were those sum of the squares within the data, so that was 22, corresponding degrees of freedom 12. So the mean square would be 22 divided by 12. And for this one, we're going to have to round it just to put something in our notes here. So I'm going to do 1.8, and I'm going to write several 3's there. So we'll do 0.8333 because I'll need that number in a second. If we round it too early, it'll throw us off accuracy for the next step. And actually, I'm going to put one more 3. So there we go. All right, so also in an ANOVA table, we often talk about total. So for the sum of squares in total, that's adding 52, and degrees of freedom would be 14. All right, so what we're going to do is take those mean squares that are attempting to estimate our variation that they have in common among the populations, and we create a ratio, and that results in our F statistic. So this F statistic is our test value in our hypothesis test. And test value, again, it's also called test statistic. So we'll keep using those interchangeably. And we haven't learned an F distribution yet, but I will do that next. So we'll talk about this F distribution. But for now, let's just go ahead and find the F statistic. So we take the mean square between the data and the mean square error, which is called the mean square within the data, and we create that ratio. So I'm just going to enter that on the calculator. So if I take 15 and divide it by 1.83333, and then I'm just going to round the F statistic to 3 places. So 8.182. And then we're going to decide if that F statistic is statistically significant. In other words, does that lead us to say we have enough evidence to support a claim that at least one population mean differs from the others? So the p-value associated with that F statistic, which we'll graph later, that p-value comes out to be 0.0057. So that's a pretty small p-value. We'll write it again on the next page, but it's looking like that p-value is low, certainly lower than alpha, like 1% or 5%, very small p-value. It's looking like we have enough evidence to support a claim that at least one of these populations does have a mean satisfaction different from the others. All right, let me show you how to get that table on the calculator. So we've got our data. So we put our data in L1, L2, L3, so that part's done. And now I'm going to actually run the ANOVA test. So all of that detail I just showed you, we can kind of move forward from it now and say the calculator can generate this for us by doing a test. So we'll hit stat tests. And the ANOVA test is the last one in that list. So I usually just scroll up to get to it faster. So there's your ANOVA. I'll hit enter. So it's on the home screen. And then I'm going to tell the calculator, I put my data in L1, L2, L3, and then enter. And at the top, you'll see your F statistic. So I know we did a lot of work to get that by hand, but now we can move forward and get our calculator's help. That p-value there is reported. And where it says factor, that's talking about the different treatments. So this is the between group variation information. So that degrees of freedom 2 we had, and then sum of the squares was 30, and MS stands for the mean square, and that's 15. So we're not going to analyze this table in detail here. But we did want to show you that an ANOVA table is just summarizing the results of an ANOVA test. And then we are going to focus on doing some problems and applying this, and also looking at our F distribution next.